So covering properties of operators, the wave packet propagation, momentum, Hamiltonian, and evolution operators. So the wave packet is a type of wave function where the wave activity travels in a burst together, and it moves as like a collective group, like within its own envelope. And in the code, some of the most important properties of the wave operator is you have to determine the initial momentum and the initial position in lines 5 and 6. And the initial momentum will have a lot of impacts on any other conditions you have in the code, whether you're doing it in free space or in a box or with a wall. It's going to affect how it interacts. The momentum operator is defined as negative IH times the partial derivative of x. And in the code in line 66, you have the initial Gaussian wave packet, but that returns individual vector values. And instead, for the momentum operator, we want a matrix. And so using the definition of a derivative, we will convert the momentum, or we will make a matrix out of the momentum operator from the vector values of the wave packet. And then in line 75, you can see that the momentum operator is in a diagonal matrix. And how we convert from a vector to a matrix is we take the individual vector values of the wave function, and then we multiply a square matrix with -1 on the diagonal time, and then also 1 on the upper subdiagonal. And when you multiply those two together, you'll get the value from the position you're at subtracted by the value of the position before that. And then you continue going down for however many values you have, and then multiply times the constants negative IH and then divide by your dx. And then here's the visual representation of the matrix. So on the left side, you have the momentum matrix, or the matrix in momentum space, and then you'll get obviously values in the diagonal. And then once you convert that to position space, you'll get a visual representation like this. And in the next presentation, Joshua will cover like Fourier transforms and how you go from momentum space to position space. The Hamiltonian operator is kinetic energy plus potential energy. In line 78, you have just the kinetic energy. And in line 110, you add the potential energy to that. And then in line 59, you define what the potential energy is. And then also in line 108, right above that, that's the Fourier transform to convert the position operator to position space and take it out of momentum space. The final thing is evolution operator. So you have the past wave function times the eigen energy states to get to your future wave function. And in the code, in line 112, you have the Hamiltonian operator being multiplied times those constants to get your energy eigenvalues. And then you multiply that times your original psi function to get your future. That's it.
Okay, please join me in thanking Wyatt. Any questions to the speaker? I do have a quick one. Slide 4, please. Yes, image on the maybe next one. Image on the right.
Yep.
Do the elements of the subdiagonal elements change as you go across the matrix, or they are the same in the vicinity of main diagonal?
In the one on the right?
Yes.
They're in the vicinity of the main diagonal.
And
but
do the absolute values, do the height of the peaks change? Just as you see it?
No.
No. How? Now let's go one back. So how does it relate to the matrix that you put on the left of this image? That on the diagonal and main diagonal you have the same numbers. Do you see a connection between this matrix and the right image on the next slide?
Yes.
Okay. Please join me in thanking Wyatt for answering questions.